In the world of modern aerial warfare, the greatest advantage isn't speed or firepower, it is invisibility. To a standard pulse Doppler radar, a traditional fighter like the F-15 Strike Eagle appears as a massive glowing target, a radar cross-section, or RCS, of roughly 25 square meters. It is a flying billboard of steel and titanium. But a fifth-generation stealth fighter, despite being 60,000 pounds of lethal machinery, registers on those same screens as something no larger than a marble or a small bird. How do you hide a supersonic jet from a multi-billion-dollar integrated air defense system? This is not a trick of light or a fictional cloaking device. It is the result of extreme physics, $150 million per airframe, and a relentless war against the laws of electromagnetics. To achieve this, engineers had to redesign every single bolt, seam, and surface to defy the way radio waves behave. Today, we go inside the skin of the world's most advanced stealth platforms. We will deconstruct the geometry of silence, the chemistry of radar absorbent coatings, and the strategic shift that rendered traditional dogfighting a relic of the past. The question isn't just how they become invisible, it's how the world's militaries plan to fight an enemy they can't even see. The fundamental challenge of stealth is the radar cross-section, RCS. Radar works by bouncing electromagnetic waves off an object and measuring the return. A standard fourth-generation fighter has an RCS between 5 square meters and 20 square meters. Through a process called specular reflection, the flat surfaces and 90-degree angles of these older jets act like mirrors, reflecting energy directly back to the source. Stealth engineering aims to reduce this signature to 0.0001 square meters. At this scale, the jet is mathematically lost in the background noise of the atmosphere. The most striking feature of a stealth aircraft is its jagged, angular shape. This is planform alignment. By ensuring that every leading and trailing edge of the wings, tail, and intakes are aligned at the exact same angle, engineers can concentrate reflected radar energy into very narrow spikes or beams. These beams are directed away from the enemy's receiver. If the radar waves don't return to the dish, the aircraft effectively does not exist. This is why you will never see a 90-degree corner reflector on a stealth airframe. Every joint is a calculated deflection. As the jet enters a high G turn, and the airframe groans under the stress, you can see the microscopic gap fillers between the panels compressing, maintaining a perfectly smooth electromagnetic surface even while the wings flex. While shape handles 90% of stealth, the remaining 10% is managed by Radar Absorbent Material, RAM. This isn't just paint. It is a complex polymer infused with magnetic iron particles. When a radar wave hits this skin, the iron particles oscillate, converting the electromagnetic energy into microscopic amounts of heat. The radar wave isn't reflected, it is consumed. However, this skin is notoriously fragile. A single scratch or a loose fastener can increase the RCS by a factor of 10, requiring climate-controlled hangars and thousands of man-hours to maintain stealth readiness. A stealth fighter's greatest weakness is its payload. So a single missile hanging from a wing pylon creates a massive radar return, negating billions of dollars in stealth technology. To solve this, weapons are stored in internal weapons bays. These bays must open, launch, and cycle shut in less than a second to minimize the radar spike during an engagement. The F-22's side bays, for example, can launch an AIM-9M in a fraction of a heartbeat, ensuring the jet remains a ghost even while it's attacking. Radar is only half the battle. To be truly invisible, a fighter must also hide from infrared search and track (IRST) systems. A jet engine's core reaches temperatures exceeding 1,500 degrees Celsius, creating a heat plume visible for hundreds of miles. Stealth fighters utilize S-duct intakes to hide the glowing compressor blades from radar and specialized 2D flat-plate nozzles on the exhaust. And these nozzles mix hot engine air with cooler ambient bypass air instantly, flattening the thermal signature and scattering the heat before a heat-seeking missile can achieve a solid lock. Behind the aircraft, the air doesn't just ripple, it tears. The focused, flat exhaust creates a distinct shimmer that dissipates rapidly into the cold atmosphere of high altitude, leaving no thermal trail for the enemy to follow. A stealth fighter that turns on its radar is like a man screaming in a dark room. You see everyone, but everyone sees you. To solve this, fifth-generation jets use low probability of intercept, LPI, radar. These systems spread their signal across a massive range of frequencies in a pseudo-random pattern. To an enemy receiver, this looks like background static or cosmic noise. The pilot sees the battlefield in high definition, while the enemy's electronic warfare suite registers nothing but quiet air. The cost of invisibility is measured in man-hours. For every hour an F-22 or F-35 spends in the air, it requires between 30 and 50 hours of specialized maintenance on the ground. Technicians must use handheld spectrometers to check for microscopic cracks in the ram coating. Even a loose screw or a bird strike can unstealth the aircraft. This creates a massive logistical tail, requiring climate-controlled hangars and specialized tape to seal every single access panel before every single mission. If you're enjoying this deep dive into military technology, consider subscribing to the channel. And before we continue, leave a comment telling us which country you're watching from. It's fascinating to see how these machines capture attention from people all over the world. The true breakthrough of the stealth era isn't just the disappearing act. It is sensor fusion. In older jets, the pilot was an operator of various independent systems. In a modern stealth fighter, the aircraft is a flying supercomputer. It collects data from radar, infrared sensors, and even the sensors of friendly ships and ground units, merging them into a single unified picture of the battle space. This changed military strategy forever. A stealth fighter no longer needs to engage in a dogfight. Its primary role is to act as a quarterback, entering contested airspace undetected, identifying every enemy asset, and painting them for long-range missiles fired from ships or non-stealth bombers hundreds of miles away. And the enemy is destroyed before they even realize a scout was in their airspace. The era of the invisible war has arrived. While no aircraft is 100% undetectable, the combination of geometry, advanced materials, and electronic silence has pushed the detection threshold so low that traditional defenses are becoming obsolete. As radar technology evolves with quantum and multi-static systems, the race between the shaper and the seeker continues. But for now, machines like this continue to redefine the balance of power in modern defense strategy. The story doesn't end here. Tell us in the comments, which military machine should we explore next? Fighter jets, submarines, aircraft carriers, or secret military bases? And don't forget to tell us which country you're watching from.